Welcome! In this session, we'll explore the problem number 1180, count substrings with only one distinct letter. We'll break it down step by step, examining the intuition, approaches, and complexities involved. Let's get started. The problem asks us to find the number of substrings in a given string S that contain only one distinct letter. A substring is simply a sequence of characters that appears contiguously within the string. For instance, in the string AA, the substrings would be A, and AA. The input to this problem is a single string S, which is composed of lowercase English letters. The output we need to produce is an integer that represents the total number of substrings meeting the condition of having only one distinct letter. To better understand the problem, let's look at an example. If the input string is AABA, the output is 8. Here's why: the substrings that consist of only one distinct letter include 6 substrings of A. These are A, AA, and AAA. Additionally, there's one substring containing just B and one more substring with A that occurs after the B. Adding these together gives us a total of 8 substrings. Another example is the string AAAAAAAAA. Here, because all characters are the same, the substrings range from single characters to the entire string. The total count of such substrings is 55. For the string AAAAAAAA, each substring length contributes to the total. Specifically, there are 10 substrings of length 1, followed by 9 substrings of length 2, and so on, decreasing until there's one substring of length 10. If we add these together, the total number of substrings is 10 plus 9 plus 8 plus 1, which equals 55. Similarly, if the input string is ABC, the substrings that contain only one distinct letter are simply A, B, and C. Since there are no repeated characters in this case, the total count is limited to 3, 1 for each character. Now let's discuss the constraints and edge cases to keep in mind. The string length, s.length, can range from 1 to 10,000, and the string will always consist of lowercase English letters. For edge cases, if the string contains only one unique character, such as AAA, the output will be the total number of substrings derived from the length of the string. For example, in AAA, the substrings are A, AAA, and AAA, totaling 10. If the string contains all unique characters, like ABC, each character stands alone as its own substring, so the total count is equal to the string's length. Finally, for very long strings, especially those close to the upper limit of 10,000 characters, it's crucial that the solution handles the large number of substrings efficiently. For example, if the input string is composed entirely of the same character repeated 10,000 times, the result will be the sum of the first 10,000 natural numbers, which can be calculated using the formula n+1/2. This ensures we can compute the output in a manner that avoids unnecessary computations, even for strings of maximum length. To begin solving this problem, we can consider a straightforward brute force approach. The intuition here is simple: generate all possible substrings of the input string S and check if each substring contains only one distinct letter. For example, if we have the string AAA, we would generate substrings like A, AA, and AAA, and check if all the characters in each substring are the same. To achieve this, we would loop through all possible starting indices of the substrings, and for each starting index, loop through all possible ending indices to form every substring. Then, we can validate if the substring contains only one distinct letter using a set or a frequency array. If it meets the condition, we increment our counter to keep track of the valid substrings. However, this method has a significant drawback in terms of computational cost. Generating substrings and validating them individually results in a worst-case time complexity of O(n) cubed, where O(n) squared is spent on generating substrings and O(n) on validation. Additionally, the space complexity is O(n), as we use a set or frequency array for validation. While this approach is conceptually simple, it becomes inefficient as the size of the input string grows. The brute force approach, while intuitive, has clear drawbacks. Its cubic time complexity makes it infeasible for larger strings, as the redundant checks for overlapping substrings significantly increase computational overhead. To address this, we can adopt an optimized sliding window approach based on a key observation: for a substring to contain only one distinct letter, it must consist of consecutive occurrences of the same character. For instance, in the string AAA, the valid substrings are AA, AAA. Instead of explicitly generating and checking every substring, we can count these substrings in a single traversal by leveraging the pattern that a group of k identical characters produces k asterisk, k plus 1, / 2 substrings. The reasoning here stems from the sum of the first k integers. To implement this, we initialize a variable count to track the total number of substrings. As we traverse the string, we maintain a count k of consecutive identical characters. Whenever the character changes or we reach the end of the string, we add k asterisk, k plus 1, / 2 to our total count and reset k to 1 for the new character group. By the end of the traversal, count will hold the total number of valid substrings. This sliding window approach offers significant advantages in terms of efficiency. First, its time complexity is O(n), since we traverse the string in a single pass, making it scalable for large inputs. Additionally, the space complexity is O(1), because it does not require any extra data structures beyond a few variables. These improvements eliminate the redundancy inherent in the brute force approach. By directly counting valid substrings based on the length of consecutive identical characters, we avoid the overhead of generating substrings explicitly, which drastically reduces computation time. This method not only simplifies the implementation but also ensures optimal performance, making it well-suited for real-world scenarios where input sizes may be large. With these considerations, the optimized sliding window approach emerges as the preferred solution. Its simplicity lies in recognizing that consecutive identical characters determine the number of valid substrings, allowing us to compute results in linear time without explicitly iterating over all substrings. By eliminating redundancy and leveraging the mathematical relationship between group lengths and substring counts, this method achieves both clarity and efficiency. While the brute force approach can serve as a conceptual starting point, it is impractical for larger inputs due to its cubic time complexity. The sliding window method, on the other hand, combines scalability with a concise implementation. The only trade-off is that the mathematical insight into substring counting may not be immediately obvious, but once understood, it provides a powerful and elegant solution. Overall, this approach balances clarity, efficiency, and optimal performance, making it the best choice for solving this problem. The problem we're solving is to count all substrings in a string where every character in the substring is identical. For example, in the string AOB, valid substrings include single-character substrings like A or B, as well as longer substrings like AAA, AA, or BB, as long as all characters in each substring are the same. To start, we'll look at the brute force approach. First, we initialize our variables. The input string is S with a length of n, and we set up a counter called count to keep track of valid substrings. Then, we iterate through all potential starting points for substrings using a loop with index I, which ranges from 0 to n1. For each starting point, we generate all possible substrings by using another loop with index j, which represents the ending point of the substring. This gives us substrings by incrementally extending from the current starting point I. Once we extract a substring, we check if it is uniform, meaning all characters in it are the same. To do this, we use a set to collect the unique characters. If the size of the set exceeds 1, we know the substring is not valid, and we stop checking further extensions from the same starting point. This helps us avoid unnecessary computations for longer substrings that wouldn't be valid anyway. When the substring is uniform, meaning the set contains only one unique character, we increment the count by 1. After examining all possible starting and ending indices, we return the total value of count, which represents the number of valid substrings. There are a few key insights to keep in mind here. First, the uniformity check using a set is efficient because a set automatically maintains unique elements. If we add characters to the set and its size grows beyond 1, we can immediately conclude that the substring is not uniform. Second, we can terminate the inner loop as soon as we detect non-uniformity. This early termination prevents unnecessary checks for longer substrings that would start with the same invalid prefix. However, the brute force method has a high time complexity because we generate all possible substrings, and for each one, we perform a uniformity check. Specifically, this approach has a worst-case time complexity of O(n), as there are O(n²) substrings, and each uniformity check involves O(n) operations. In terms of space, we use a set for uniformity checks, which requires n space in the worst case when the substring length equals n. One way to optimize the brute force approach is to avoid explicitly creating substrings. Instead of extracting substrings and storing them in memory, we can directly compare characters within the nested loops. This eliminates the overhead of substring creation, making the algorithm more efficient. Additionally, a more advanced optimization involves using the sliding window technique. With a sliding window, we dynamically adjust the bounds of a window to count contiguous substrings with the same character. This optimized approach significantly reduces the complexity to n, as we no longer need nested loops to examine all possible substrings. To illustrate the brute force process, let's consider an example with the string s equals aob. Starting with I equals 0, we examine substrings by incrementing j. At j equals 0, the substring is a, which is valid because the set contains only one character, so we increment the count to 1. At j equals 1, the substring aa is still uniform, so the count becomes 2. This process continues for substrings AAA and AAAA, increasing the count to 4. However, when j equals 4, the substring becomes aob, which contains both at and b, so the set size exceeds 1, and we break the inner loop. We repeat this process for starting indices I equals 1, I equals 2, and so on, evaluating all possible substrings. Edge cases are also important to consider. For instance, in a single character string like s equals a, the only substring is a, which is valid. In a string with all unique characters like s equals abcd, only the single character substrings are valid, as no multi-character substring can be uniform. In an empty string, there are no substrings, so the result is 0. On the other hand, for strings with long repeated characters, such as s equals AAAA, every possible substring is valid, leading to a high count. Finally, let's analyze the complexity of the brute force approach. As mentioned earlier, the time complexity is n cubed, due to the nested loops in uniformity checks, while the space complexity is n, because of the set used for those checks. To implement this in Python, we use two nested loops to iterate over all starting and ending indices. A set is used within the inner loop to track unique characters, and the count is increment whenever the substring is uniform. For example, with s equals aob, the function outputs 12, which is the total number of valid substrings. This solution efficiently counts substrings with only one distinct letter in the input string s. The function starts by initializing count to 0, which accumulates the total number of valid substrings. We also determine the length of the string n and set up a pointer I to iterate through the string. The algorithm uses a while loop to iterate through the string. For every character at position I, a nested while loop is used to find the length of the contiguous segment of characters that are the same. This is achieved by incrementing a second pointer j until the character at j differs from the character at I or the end of the string is reached. Once the contiguous segment's length is identified, the number of substrings that can be formed from this segment is calculated using the formula length plus 1 / 2, which sums up all substrings of lengths 1 through length. This result is then added to the count variable. Finally, the outer pointer I is moved to the end of the current segment, j, and the process repeats until all characters in the string have been processed. The function returns the total count of substrings as the result. This approach is efficient, with a linear time complexity of n, as each character is visited at most twice. Here, we have the Java implementation of the solution. The method countLetters takes a string s as input and returns an integer representing the total number of substrings that contain only one distinct letter. We start by initializing a variable count to 0, which will store our result, and n to the length of the string. A pointer I is also initialized to 0 to traverse through the string. Inside the while loop, we use another pointer j to identify segments of consecutive identical characters. The inner while loop increments j as long as the current character at j matches the character at I. Once the segment ends, we calculate its length as ji. Using this length, we determine the number of substrings that can be formed with this segment using the formula length plus 1 / 2, which is then added to count. Finally, the pointer I is updated to j to move to the next segment. After processing all segments of the string, the method returns the accumulated count. This implementation ensures that we efficiently count substrings with only one distinct letter by leveraging the mathematical formula to calculate sums of sequences. The two-pointer approach helps us traverse the string in linear time, making the solution optimal for this problem. Here, we start with the input string s equals AAA. First, we initialize our variables. Count is set to 0, which will store the total number of substrings with only one distinct letter. The length of the string n is calculated as 3, and we initialize a pointer I at 0 to track the beginning of a segment with one distinct letter. Next, we enter the outer while loop, which begins with I equals 0. We also set another pointer, j, equal to I. The inner while loop then expands j as long as the character at j equals the character at I. Since all characters in this segment are a, j increments until it reaches 3, marking the end of this segment. The segment length is calculated as ji, which is 3. To find the number of substrings in this segment, we use the formula length asterisk, length plus 1, / 2, resulting in 6 substrings. We add this to count, updating it to 6. Finally, we move I to j to check the next segment, setting I to 3. Since I is now equal to n, the outer while loop ends, and the function returns count equals 6. Now, let's examine the input string s equals ob. We initialize count to 0, calculate the length of the string n as 3, and set the pointer I to 0. Entering the outer while loop with I equals 0, we set j equal to I. The inner while loop expands j as long as the characters at j and I are the same. For the first segment, consisting of 2as, j advances to 2. The length of the segment is calculated as ji, which equals 2. Using the formula length asterisk, length plus 1, / 2, the number of substrings in this segment is calculated as 3. We add this to count, updating it to 3. After processing this segment, we move I to j, setting I to 2 to check the next segment. At this point, I is 2, and we continue with the input string s equals ob. In the outer while loop, we set j equal to I. The inner while loop then expands j as long as the characters at j and I are the same. For this segment, which consists of a single b, j advances to 3. The length of the segment is calculated as ji, which equals 1. Using the formula length asterisk, length plus 1, / 2, the number of substrings in this segment is calculated as 1. Adding this to count, we update it to 4. We then move I to j, setting I to 3. With I now equal to n, the outer while loop ends, and the function returns count equals 4. For the input string s equals abc, we start by initializing count to 0, calculating the length of the string n as 3, and setting the pointer I to 0. Entering the outer while loop, we set j equal to I. The inner while loop expands j as long as the characters at j and I are the same. For the first segment, consisting of a single a, j advances to 1. The length of the segment is calculated as ji, which equals 1. Using the formula length asterisk, length plus 1, / 2, the number of substrings is calculated as 1. We add this to count, updating it to 1. We then move I to j, setting I to 1 to check the next segment. Now, with I set to 1, we process the next segment in the string s equals abc. Setting j equal to I, the inner while loop expands j as long as the characters at j and I are the same. For this segment, consisting of a single b, j advances to 2. The length of the segment is calculated as ji, which equals 1. Using the formula length asterisk, length plus 1, / 2, the number of substrings is calculated as 1. Adding this to count, we update it to 2. Moving I to j, we set I to 2. Now for the final segment, j is set to I. The inner while loop expands j as long as the characters at j and I are the same. For the segment consisting of a single c, j advances to 3. The length of this segment is again 1, and the number of substrings is calculated as 1. Adding this to count, we update it to 3. Finally, with I set to 3, the outer while loop ends, and the function returns count equals 3. The time complexity of our solution is O, n, where n is the length of the input string. This efficiency is achieved by how we traverse the string using two pointers, I and j. The outer loop, controlled by pointer I, processes chunks of identical characters, and after processing each segment, I skips directly to the next segment. This ensures that every character in the string is visited exactly once, contributing an O(n) complexity for the outer loop. Now, even though there's an inner loop controlled by j, it doesn't increase the overall complexity to quadratic. This is because the inner loop simply counts the length of the current segment and stops when the segment ends. Across all segments, the total work done by the inner loop is proportional to the total number of characters in the string, which is still O(n). Additionally, the formula, length plus 1, / 2 used to calculate the substrings for each segment is a constant time operation. Combining these factors, we conclude that the overall time complexity is O(n). The space complexity of this solution is O(1), meaning it uses constant space regardless of the size of the input. This is because the algorithm only utilizes a few integer variables, such as count, n, I, and j, to manage indices and counts during the computation. These variables do not scale with the input size, they occupy the same amount of memory no matter how long the string is. Furthermore, the solution avoids using any additional data structures like arrays or hash maps, which would otherwise increase memory usage. Since the memory requirements remain fixed and independent of the length of the string s, the space complexity is classified as O(1). When comparing our optimized approach to the brute force method, the difference in efficiency becomes clear. The brute force approach involves generating all possible substrings of the input string and then checking each substring to see if it contains only one distinct character. Generating all substrings alone takes O(n², and verifying each substring's distinctness adds another O(n), leading to an overall time complexity of O(n³). In contrast, our optimized solution avoids generating substrings altogether. By grouping contiguous segments of identical characters and directly calculating their contribution using the formula, length plus 1, / 2, the time complexity is reduced to O(n). This improvement holds true across all cases. Whether the string contains all identical characters, a mix of identical and distinct characters, or all distinct characters, the algorithm processes each character exactly once. Therefore, the time complexity remains O(n) in the best, average, and worst cases. Mathematically, we can confirm the time complexity of O(n) by analyzing the total number of iterations. Let the input string have n characters and k contiguous segments of identical characters. The outer loop runs k times, corresponding to the number of segments, and the inner loop processes each character in a segment. Importantly, the inner loops do not overlap, meaning each character in the string is part of exactly one iteration of the inner loop. Thus, the total number of iterations across all inner loops is equal to n. Operations like arithmetic calculations, such as length plus 1, / 2, are constant time operations and do not impact the overall complexity. Combining these observations, we can conclude that the total time complexity of the algorithm is O(n). When solving this problem, there are several common mistakes to watch out for. First, not identifying constraints early can lead to inefficient solutions. For example, if you forget to consider the maximum string length or the type of characters, you might end up writing a brute force solution that won't scale for strings of size 10 to the power of 5. Next, overlooking edge cases is another frequent issue. Scenarios like an empty string, a single character string, or a string where all characters are identical can easily trip up your solution if not accounted for. Another pitfall is inefficient substring generation. Explicitly generating substrings using nested loops can lead to O(n³ complexity, which is highly inefficient for large inputs. Instead, techniques like sliding window or two pointers can significantly optimize performance. Additionally, errors can arise from incorrectly counting distinct characters. For instance, using a basic counter instead of a set, or failing to reset it properly, might lead to incorrect results. Finally, ignoring space complexity is a mistake to avoid. Using large data structures like arrays or hash maps unnecessarily can increase memory usage, so it's better to opt for in-place solutions or smaller auxiliary structures whenever possible. Now, let's focus on some key interview insights related to this problem. Recognizing patterns is crucial. Many substring-related problems rely on techniques like sliding window or dynamic programming. Being able to quickly identify and apply these patterns can give you a significant advantage during interviews. Additionally, interviewers often expect you to discuss trade-offs between time and space complexity. For example, a sliding window approach generally offers better time complexity but might require a bit more memory. Another important aspect is explaining how your solution handles edge cases. This level of clarity demonstrates that you've thoroughly tested your approach and thought through potential pitfalls. Finally, relating the problem to real-world applications can leave a strong impression. Substring problems are highly relevant in areas like text processing, search engines, and data compression, so drawing these connections can highlight your understanding of practical applications. If you want to practice further, consider exploring related problems such as longest substring without repeating characters, longest repeating character replacement, or minimum window substring. These all share similar underlying techniques and can help you solidify your skills. Let's explore some alternative approaches to solving this problem. The sliding window technique is a popular choice, as it efficiently tracks substrings while maintaining a window of valid characters. This approach often reduces complexity to O(n), though it may require additional space for a hash map or set to track characters. Another option is dynamic programming, which is particularly useful when there are overlapping subproblems, like counting substrings with specific properties. The trade-off here is that DP typically uses more space for tables but can simplify the implementation. Hash maps or sets are another viable approach, explicitly tracking character counts or distinct characters. While slightly slower than sliding window methods, this approach is easier to implement and understand, especially for beginners. Lastly, there's the brute force approach, which systematically examines all possible substrings. However, this method is only feasible for small input sizes because its O(n)cubed complexity becomes impractical for larger strings. Choosing the right approach depends on the problem constraints and the balance between time and space efficiency you're aiming to achieve. Great job! To recap, we explored the problem, discussed various approaches, and highlighted key insights. Keep practicing similar problems to improve your skills. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!